want to just work out an example to discuss a little bit more what we talked about in the last example, or in the last video. So here I've got this function. Z is a function of two variables, x and y. It's tangent of x times y. I've got a point P naught in its domain, and I want to find the tangent plane at P naught. And I could pretty easily see that this function is going to be continuously differentiable with respect to both variables, so it's differentiable so that the tangent plane will exist. So now I need to say, okay, finding the tangent plane. Am I working with the entire graph of the function, or with just a part of that, a subset of the domain? Well, the graph of this function would be in 3 space. It's a surface in 3 space. Surfaces in 3 space can have tangent planes. If I were to restrict myself to a level thing, in this case it would be a level curve, that would drop me down to 2 space. Curves in 2 space don't have tangent planes, they have tangent lines. So I'm working with the entire function, so I would be finding my local linear approximation. So I know L of xy is f at P naught plus the gradient of f at P naught dotted with, it'll be x minus pi, y minus 1/4. Okay, so let's just find the pieces to fill them in. Notice, setting this equal to L of xy, that tells me we are in 3 space because that's giving me my z values. This is also, I mean, this is just a number, but this is giving me the z value at my point of tangency. Okay, so f at pi 1/4 is just going to be tangent of pi over 4. That's just 1. Gradient of f, that's the partial with respect to x, comma, partial with respect to y. That's going to be y secant squared xy, comma, x secant squared xy. So the gradient of f at P naught is, we're plugging in 1/4 for y times secant squared of x times y. Now x times y was pi over 4. Cosine of pi over 4 is root 2 over 2, or if it didn't simplify, it's 1 over root 2. So secant's going to be the reciprocal. Secant of pi over 4 is root 2, and then when I square that, I'll get a 2. And then x was pi, and we're multiplying that by secant squared as well, so also by 2. So we're basically getting 1/2 2 pi. Okay, so I can plug in those pieces. We get L of xy is equal to 1 plus 1/2 2 pi dotted with x minus pi, y minus 1/4. Let's just work it out until we don't have any vectors in that equation. So L of xy is equal to 1 plus 1/2 of x minus pi plus 2 pi times y minus 1/4. Excellent. I'm going to keep that up here. I want to just show you, though, that we could get the tangent plane another way. If you prefer to get things in point normal form, you can, but you're going to need to make a modification here. Because for point normal form, we're saying what's normal to things is generally the gradient. But I know the gradient of f, that was this right here, that's a vector in 2 space. That's not going to be normal to the graph of the entire function. That's going to be normal to its level curves. So what I would need to do is create this new function. I'm going to call it g of xyz. Let's let it be f of xy minus z. Okay. So that's going to make it tangent of xy minus z. Now that's a function of 3 variables. And if z is equal to tangent of xy, which is what's true on the graph of this function, I'm looking at the level surface, tangent of xy minus z equals 0. So anytime you have z equals a function, that function minus z will equal 0. So I can go from thinking about the graph of a function of 2 variables to a level surface for a related function of 3 variables. Okay. I can always do this. Given an equation for a level surface of a function of 3 variables, I may or may not be able to solve for z to get to a function of two variables. In this case, it would be very easy to solve for z, but we've certainly encountered equations where we had a level surface, but it wasn't the graph of a single function, and so we weren't able to solve for z. Okay, but we can always go in this direction. Now, once I have this, when I'm talking about a level surface, what's normal to that level surface is the gradient of this function. And the gradient of this function will be a vector in 3 space. So, I'm going to have a point and a normal. Now for my point, it's going to be related to this point P naught, but it has to be a point in 3 space. So that would be Q naught pi 1/4 1, where that z value is that same one right there. That's f at P naught. Okay. So basically P naught comma f of P naught, that's a point on the graph of this function, and the graph of this function is the same as the level surface for this function. Okay, then my normal will be the gradient of g evaluated at Q naught. So the gradient of g is just g sub x, g sub y, g sub z. Now g sub x, well, since the x's only show up right here, the partial of g with respect to x is exactly the same as the partial of f with respect to x. And we said that was y times secant squared xy. Same thing for the partial of g with respect to y. The only y that shows up is in this part of my formula from f of xy, so I'm getting the same partial derivative there, x secant squared xy. Partial with respect to z, -1. If I look at the gradient of g evaluated at pi 1/4 1, when I plug in to this point, that's going to give me 1/2. That's going to give me 2 pi, and of course that's constant at -1. Notice the first two components of the gradient for g are the components of the gradient for f. So they're related to each other, but that's a vector in 2 space, and that's a vector in 3 space. They're connected, but they are very, very different. Okay, but now I can say that if I were to let Q represent an arbitrary point in 3 space, x, y, z, I can say that n dotted with Q naught Q would have to equal 0. But my normal vector is this gradient, 1/2, 2 pi, -1, dotted with. This would become x minus pi, y minus 1/4, z minus 1. And that's got to equal 0. If I work out that dot product, I'm getting 1/2 x minus pi plus 2 pi y minus 1/4 minus the quantity z minus 1 is equal to 0. Now, is this plane the same as this plane? Yes, it is. Remember, L of xy was just a fancy name for z. So if here I distributed this negative, it becomes a minus z and a plus 1. There's my 1. I've got plus 1/2 x minus pi. I've got plus 2 pi y minus 4, and I could add the z over to the other side. So they're equivalent representations of the plane, but I just need to be very careful that if I'm using point normal form, I'm working with a level surface for a function of 3 variables. If I'm working with the local linear approximation to get a tangent plane, I'd better be working with the graph of a function of 2 variables.